Alright, so we left off with measures of center, mean, median, mode. But we saw that we could have multiple data sets that had very similar measures of center that look drastically different from each other. So another tool in the toolbox is looking at measures of variation. First and most basic measure of variation is the range. It's very quick, and it gives us an idea of how spread out our data values are by looking at the minimum and the maximum. We've used range when we were making our histograms in order to find our class width, things like that. But it also is useful when giving us an idea of how spread out an entire data set is. The difference between the minimum and the maximum. Okay? When we look at Corporation A, we've got 10 graduates starting out in Corporation A, and they are paid the salaries listed on that table in thousands of dollars. So we have someone making $51,000, someone making $48,000, $49,000, okay? I need my minimum and maximum values. What's the minimum of salary for company A? $47,000. And what's the maximum? $57,000. That's right, maximum. Okay. So we take the maximum and the minimum, and we find the difference. So what is the range in the salaries? $10,000. Okay. So we have a range of $10,000 for company A. What about for company B? What's the range of salaries for company B? Okay, 68 less 33 gives us a range of $35,000 in the salaries. Now, both of those companies can advertise the same median salary of $51,000. We see that in these two histograms listing out the 10 salaries for each company. They both have the same mean of 51.5. They both have the same median of 51. They both have the same mode of 51. The measures of center for all, or for both of those companies is the same. But because the range is different, it shows us the variation in those different salaries. Okay? So we can see that there's a stark difference. Most of the companies, or most of the employees in Corporation A are making somewhere around that median value of 51. Most of them are making 51,000. And while we have a few people in Company B making about 51,000, we also have a third of them making significantly less and a third of them making significantly more. So the two sets of data have a lot of variation to them. Now, the range doesn't give us a full picture. Range can often be thrown off by the existence of outlier data, which usually causes a problem. And again, it only takes 2 data points into consideration. So something that can be much better measure is our deviation, which is used to calculate variance and standard deviation. Deviation just measures the difference between any given data value and the mean. Okay? So every single data point is going to have its own deviation from the mean. We use deviation in calculating variance, and then we use variance in finding our standard deviation. And we're going to spend most of our time looking at standard deviation. So when we have a population data set, our deviation is going to be our data point subtracted by the mean, that's mu. If it's a sample, it's a data set subtracted by, that should be x bar, for the mean of the sample. So the data value minus the mean of the sample. That gives us this value in here for our formula for variance and for standard deviation. Okay? That's the deviation. We have to find that deviation for every single data point. Using that deviation, what we end up doing is we square all of those deviations and then add them up together. So we find our deviations, we square it, we add it all up, and then we divide by our population. That gives us the variance. Once we have the variance, we square root it. That just gives us our standard deviation. So there's just one step left to do. Some things to note about standard deviation. Okay? Variance could give us an idea of how much there is in varying of our data set, but unfortunately, it doesn't give us any concrete information because the units are different. Okay? Because we square the data values. We square that deviation. So the units on variance are different than the units in our data set, so doesn't have a concrete use. But it's necessary for standard deviation. Once we square root it, then we end up getting a value that has the same measurements or the same units as the data set. And it tells us how far each data value, on average, is away from the mean. So it's always going to be positive. It's always going to be greater than or equal to 0. If our standard deviation is 0, that means that all of our data points are the same. There is no variation. Everything's the same. As our entries get further and further away from the mean, meaning that they are more spread out, then our standard deviation gets larger. So it's another tool in our kit for helping us look at that spread. But we also have to kind of combine it with different things, such as the range and the median, to get a really big picture, because as we get increasingly large numbers or increasingly small numbers, those different scales of magnitude can have an impact on those different measures. So for finding variance and then standard deviation is a pretty straightforward 6-step process. The first 3 steps are pretty tedious, okay? But I'm going to break them down. And it's really important for you to understand kind of where these come from. So the first step is to find the mean of the population set. That's mu, or x bar, depending on which formula we're using. So we start with the mean. Then with the mean, we find the deviation of every single data entry. The deviation for each entry. So for every single data value, I'll subtract the mean, and I get a number. Positive or negative. If my deviation is positive, then that data entry is above the mean. If my data entry, or if my deviation is negative, then my data value is lower than the mean. Okay? So that tells us how far above or below the mean. That is this part of the equation, x minus mu. That's deviation. Once we have all of those deviations, we then square each of those deviations. And I'll explain why we square it in a little bit. Okay? Square each deviation. That's that part. That's step 3. Step 4 is to then add up all the square deviations. We find the sum of the squares. That's the summation right here. Okay? Sum of squares. You'll also often see this listed as SSX. It means the sum of the squares of the deviation. In data analytics, it's referred to the sum of squared error. So that deviation is squared error. Then, in order to get our variance, the last step is just divide by our population size. We're going to divide by the population size. That gives us the variance. And then when we square root it, that gives us the standard deviation. The formula for finding standard deviation of a sample is very, very similar with one slight difference, and we'll cover that when we get to the sample. So we want to find the population variance and the standard deviation for the starting salaries for just Company A. We're going to use Company A. And so the first thing we have to know is what? What's the first thing we need to have in order to do standard deviation? We need the mean. Okay? They told us the mean on the last one, so we don't need to calculate it again. Our mean was 51.5. Okay, so there's our mean, 51.5. Step 2, we want the deviation. So we're going to take every single x value, and we are going to subtract the mean. So we take 51, and we subtract 51.5. What do we get? 8.5. So we get negative 0.5. And then we do it again. 48 minus 51.5. What do we get? Say it again. Negative 3.5. And then we do it again. 49 minus 51.5. It's 49 minus 51.5. 55 minus 51.5. 57. 51. 54. Again. So that's that negative 0.5. 47. And 52. So all of our deviations. So 51 is 0.5 below the mean. 48 is 3.5 below the mean. 49 is 2.5 below the mean. 55 is 3.5 above the mean. 57 is 5.5 above the mean. Now, what I want you to do is I want you to take all of those deviations and I want you to add them up. All those deviations, add them up. It's the mean. You got 0. Anyone else get 0? That's right, it's 0. The sum of our deviations will always be 0 because it's based off the mean and we're trying to find how far apart every data value is, and if it's not 0, then it's not your mean. You'll have the same amount of variation above as you will below your mean, otherwise your mean is not in the center. Okay? Because of that, that's why we have to do the sum of squared errors. The sum of my errors just gives me 0. That doesn't do anything for me. So we have to use a little mathematics, and we use the sum of the squared errors. So we take negative 0.5 and we square it. What do we get? Positive 0.25. Yep. So your squared errors will always be positive, so that when we sum up our squared errors, we'll actually have a useful number. Right, ladies? Okay? So, negative 3.5 squared. 3.5 squared. More than 9, but less than 16. 12.25. Alright, go ahead and get the rest of those squared deviations and add them up. Alright, what is the sum of our squared error? Okay? So we add up all of our squared deviations, we get 88.5. So that is the numerator of our formula. The sum of the squared deviations, the sum of the squared error. Now we need to divide by our population. What's our population size? So what's our variance? 8.85. Okay? And then our standard deviation is just the square root of our variance. So we take our variance, 8.85, and we square root it, and we get approximately what? Okay. So let's round it up to just 3. Just to make it easier to explain. Okay, so our standard deviation is 3. So typically, our data points vary 3 units above or below our mean. So 51.5 thousand, our standard deviation says that most of our data points will vary $3,000 above or below the mean. That's standard deviation. It's the most common measure of variation is standard deviation. Yeah. On the chart or the map? The sum of the squared errors divided by the population to get the variance, and then you square root it to get your standard deviation. Your math was right, you just used the wrong number. Alright, so same idea but with a sample. The formula is exactly the same, except instead of using the sample size, we do the sample minus 1. We use sample minus 1. A bunch of people way smarter than me, at least as far as statistics goes, a long time ago, found out that when calculating a standard deviation based off of a sample, for some reason, I don't know why, it was more accurate if they used 1 less than the sample size, and it was more closely or more accurate compared to the population standard deviation, rather than just using the sample size. Okay? I don't know why. Someone wrote a proof about it. It works. That's all we need. So sample standard deviation is the same exact process, but instead of dividing by the entire sample size, we'll divide by 1 less than the sample size. Now, standard deviation is a very tedious process. Okay? I don't expect you to do a tedious process as long as you have the right tools to do it for you. So, on our fancy dancy calculator, we have a nice little button that says stats. And we can use that to calculate several different things, including standard deviation. When we go under stats, we can go to edit, and we get lists. If you've got something in the list, you can clear it out. And what we can do is we can input our data set into this list. And so I'll type in 8 and hit enter, and I'll type in a 10, and I'll hit enter, and I'll go through for all of my data points. And I want to make sure that when I'm putting in my last data point, I have the correct number. So this says for list 1, data point number 12 is an 11, and I want to make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have the correct number of data points. That way, you check to make sure you put in hopefully the right number of numbers. Whether they're the right numbers, I would go back and double check. But data point number 12 is an 11. I hit enter. Okay? Data point 13, I'm going to leave blank. Once I've got my data set in there, and you can put in multiple data sets, you go back to stats, and then we go over to calc. And we're going to calculate one variable statistics. I'm going to tell it which list I want to use. I'm going to use list 1. And so I just hit enter, enter, enter. And it's going to give me a whole readout of a bunch of different statistics. Right at the top, X bar. What does X bar mean? What's X bar? Say again. The mean, population or sample. So we have a sample mean of 7.5 for that data set. We have a sum of our data values, 90. We've got sum of data squared. We have our standard deviation, sample and population. S for the sample, and then we've got our population standard deviation. N is the number of data values. We'll talk more about min, Q1, Q2 later on, but we see the minimum value is 4. We see our median value is 7. We got a maximum value of 11. So it gives us a lot of information in there. We can use our minimum maximum to calculate our range. We've got our median. And so we've got a lot of different statistics there. So since we're dealing with a sample, and we want the sample variance and the sample standard deviation. So we want our variance, which is standard deviation squared, and we want our standard deviation, okay? So, actually that's not the sample one, that is S squared and S. For sample standard deviation and sample variance, okay? So our sample standard deviation is this 2.153221688, and it keeps going. Okay, that's standard deviation. We square root it. It's going to be irrational. So we can round it to 2 data points. 2.2, approximately. So I have a standard deviation of about 2.2. We'll talk about what that means in a second. If I want to get my variance, what can I do with my standard deviation? Square it, okay? So I've got, let's do it before we round. We've got 2.153, 2.153, and we square it, and round to 1 data point, or to 1 decimal, 4.6. So we have a variance of about 4.6, and our standard deviation is 2.2. So we look at what it is that we're actually dealing with, what our data set says, and so we have high school football players who got a concussion, and the amount of days it took for them to recover from that concussion. The average was 7.5. We got that from our table. The mean was 7.5 days for recovery. With a standard deviation of 2.2, that means that most of those students recovered somewhere within 2 days of 7.5. Either 2 days more, 2 days less than that mean time. So most of them recovered in around 5 to 9 days. That's what our variation tells us. How far away from the center? So our calculator will do a lot of this for us. If you don't have a calculator to do that for you, there's your formula. Most of the time what we do is we just need to be able to interpret and analyze standard deviation. Physical software that does all this stuff for us. So we don't need to do all the tedium. It's important to understand where the tedium comes from, how we're getting these values. But after that, it's more important about what it's measuring. So measure the typical amount an entry deviates from the mean. How much it deviates, standard deviation. The more they're spread out, the larger our standard deviation. 3 different data sets with the same mean. 5, but with different deviations. When we see that we have a standard deviation of 0, well, there's none. There's no deviation. All of my data values are 5. But as we increase our standard deviation, we see that our values start to spread out more and deviate from the mean. Now, most of them are still 5. They're not very far from 5, so my standard deviation is 1.2. Most of my data points are within 1.2 from the mean. 1.2 is right about there. So most of my data set's still there, close to my mean. As I increase my standard deviation to 3, my data points get more spread out, even to the point where now none of my data points are actually my mean value. They've spread out so far that my standard deviation is now 3. So we can look at frequency distributions, and we can look at histograms, and we can estimate around what the standard deviation is going to be without doing any calculations to figure out how spread out something is, what has bigger standard deviation versus something else. So if I've got a sample or a population of 8 and I've got a mean of 4, and all my data values are 4, what's my standard deviation? 0. There is no standard deviation. There's none. Okay? So I have a standard deviation of 0. Now when I look at data set 2, I still have a mean of 4, but none of my data values are 4 now. They're all 3 or 5. So how much are they varying from our mean? They're not varying by 2. They're varying by 1. 1 above and 1 below. They're varying 1 above and below. All entries are plus and minus 1 from the mean. So our standard deviation is about 1. When we look at that third data set, we have more variation. How would you describe the way the data is varying and how far away it is from our mean? Some of them are 3. What about the other half? That's 1, right? So half of the data, half of the entries are plus and minus 1. I've got 3 and 5. The other half is plus and minus 3. 1 and 7. So my standard deviation is talking about all of it. So on average, how far does my data deviate from my mean? Half of it is 3. We want to meet somewhere in the middle. More or less. What's the midpoint of 1 and 3? 2. So our standard deviation is probably going to be around 2. It's not exactly 2, but it's close to 2. If we calculated the actual standard deviation, it ends up being 2.2. But we can still get a good idea about the estimate by looking at the dispersion among the data. Questions, comments, concerns, queries, or... We're going to take a break here. We'll cover an empirical rule tomorrow. But you can start on your assignment now, and you should be able to knock out a decent amount of it before we even leave. I had someone first period finish all the way through this part in 10 minutes. So, knock out a significant part of it. Sure, go for it. So you go to stat.